Right. Good afternoon, everyone, or morning, or whatever time it is. Welcome back to Advanced Geometry Lectures. Today, I think what I will do is I'm just going to go through some IMO problems, specifically the easier ones, so level 1s and level 4s, because I think it probably be a really good idea for you guys to see what IMO level problems actually look like. So I will start with 2013 problem 4, I will do 2014 problem 4, and I will do 2015 problem 4, and if we have time we will do 2016 problem 1. But like I said, we're going to start with 2013 problem 4, and I will also go through making the diagram for at least the first one, maybe not the second and the third, it depends on how much time we've got. And yeah, so I will just go through the solution and tell you how I think about things, and hopefully that will give you some idea of how you can approach geometry problems in tests and Olympiads and etc. So let's get on with it. So first thing I guess I should do is I should probably show you the question. So this is the question here. So if you basically what you've got is you've got an acute angle triangle ABC with its orthocenter H, and we have a point W on the side BC, which is strictly between B and C. We also have points M and N, which are the feet of the altitudes from B and C respectively. And then we have two circles. We have omega 1 and omega 2. The omega 1 is the circumcircle of BWN, and omega 2 is the circumcircle of CWM, and then we define points X and points Y on omega 1 and omega 2 respectively, such that WX is the diameter of omega 1 and WY is the diameter of omega 2, and then the idea is to show that X, Y and H are collinear. So to go about constructing this, we think, okay, well, firstly, we might need a circumcircle at some point, so let's draw a circumcircle. We might not need this, but it's a good thing to use. And then we construct a triangle. Whoops, hang on, let's do this now so we don't have to bother about it later, and just rename this to O, and rename this point to something we're never going to use, like no, not, let's call it not, and then let's not show it, get rid of that now. And then we construct our triangle, A, B, C. Then we have W on BC, lying strictly between B and C. Now, they didn't actually specify anything about this, so we are just going to take the fact that it is variable, so it's arbitrary, it doesn't tell us anything. The points M and N are feet of the altitudes from B and C. Okay, so that means we're going to need perpendicular lines from B and C. And these are M and N. M and N. Oh, for God's sake. Hang on a second. M and N. There we go. Now we just define circumcircles of B, W, N and C, W, M, and then we want diameters. Now, what you would have done in constructing this is you would have had a compass, so you would have some idea of where the diameter is. In this case, I actually do not, so I have to be a bit careful here, but we can just get the circumcenter by doing perpendicular bisectors. Let's just do that, and then we draw the line through there. Then let's hide, oops, hang on. So let's hide this one, and let us hide this one. And then we do the same thing for the other side. There's this one and this one, so we have a point there. I'm interested in seeing those, and then we just draw the line. And that gives us the point here, which is x, and this point here, which is y. And let's rename that x, and this one is y. And we have h, which is the orthocenter. So this is going to be the orthocenter here. Now, we want to show that x, h, y arc, they all lie on a line. Now, if you've drawn a neat diagram, which of course we have here because we're using a computer, you will see that x and this intersection of these two circles and y are collinear. This is a pretty easy lemma to prove. Simply, if we just construct a point there, say call it F, then we draw the line W. F. Now, then we draw the line ED. We know that because these are two circles that intersect at F and W, and E and D are the centers of these two circles, that the line ED bisects the line FW. Specifically, it bisects it perpendicularly. And we also know that XE is equal to EW because they're both radii, and WD is equal to WE. DY. Also, same reason, they're both radii, which means we can use midpoint theorem to show that ED is parallel to XY, and furthermore, we also have that this is a perpendicular bisector, which means that EG is parallel to XF, GD is parallel to FY, and therefore XFY is just a straight line, because both parts of it are parallel to a single straight line. So the idea we are going to show is that the angle HFW is 90 degrees. And if the reason why we're going to do this is if we can show that HFW is 90 degrees, then we know that X and H and Y must lie in a straight line because we know that XFW is 90 degrees. Well, we know that H is the orthocenter, which means that if we drop a perpendicular line from H to the base BC, it's going to go through A, and we know it's 90 degrees over there. So the idea would be to, let's call this point something. Let's call it, not I, because I is a terrible name for a foot, so let's call it K. And so the idea would be to show that HFWK is a cyclic quad. And the way we're going to do this is first we're going to move this W around a bit so we can see our diagram a bit better. And I think the way we are going to do this is to show that WFA is collinear. Is that a thing? Let's see. It is a thing. And then use power of a point. That seems like the best way to do it. Alternatively, we can chase some angles. But I'm not sure which angles we would chase. So let's take a look at this. Actually, it might be an angle chase. So that's a... So... Hang on a second, let me just pause this for a second. Oh, that's weird. Okay, no pause. I can't quite remember how I did this before. Okay, well, let's just firstly go about proving that WF does in fact go through A. That shouldn't be too difficult. So, okay, yes, okay, so yeah, this is how it's done. So we're going to use PowerPoint for the first time, which is really good because I think it's important that you see how to use PowerPoint. And specifically, we are going to first look at the circle that goes through the points N, B, C, M. Now, you should already know that the circle that goes through N, that there is a circle that goes through N, B, C, and M. And for ease of viewing this diagram, I'm going to make it a dotted line and make it a bit smaller so you can, so it's not too glaring. Well, there's a lot of lines here. Okay, so you should know that this is a cyclic quad because we've got two angles subtended at 90 degrees. Now, we will look at the power of A with respect to this circle. Now, the power of A with respect to this circle is given by the value. Let me find text, and let's get rid of these settings. We're not going to need that for now. It's given by the value CM, not CM, what am I talking about? CA times AM. And we know that it's also equal to BA times AN. That is what is known as power of a point. Now, we know that the radical axis of two circles is precisely the line that it runs between the intersection points of two circles. So if we've got two, so hang on, let me just open another window so you can see what I mean. Let's do duplicate here. So let's talk about quick interlude with PowerPoint. So if we've got two circles, let's go with that. Two circles like that, then the power of every point on this line with respect to both circles is the same. At this point, you should have seen power of a point. If you haven't seen power of a point, then you can ask me about it in the Q&A session, but at this point, I kind of have to assume that you have seen it. And so, basically, if we draw any line from through this circle here, and then we get a point here, and then we draw that line there, we will get a couple other points, and we have the text EG times GF is equal to HG times GI. This is true for every point G on this line. So no matter where I draw this, that ratio is going to be true. Well, not that ratio, that equation is always going to be true. So going back to this, let's see how that's applicable. So we look here, and we get that CA times AM is equal to BA times AN. However, we also know that A lies on the, so I could put it this way, the power of point A with respect to this dashed circle here is this value here. But we also know that A lies on the radical axis of this dashed circle and the circle on the right, which is omega 2. But it also lies on the radical axis of this dashed circle and this circle here, which is omega 1, which means the power of point A with respect to the dashed circle is the power of point A with respect to omega 1, as well as the power of point A with respect to omega 2, which means that the power of point A with respect to omega 1 and omega 2 is the same, which means it lies on the radical axis of omega 1 and omega 2. Therefore, it must lie on the line that passes between the two intersection points, which is precisely WF, which means that is a straight line. And furthermore, we also know that there is a circle here that passes through N, B, and K, which passes through H, and similarly a circle that passes through C, M, and K, which goes through H. That is a very well-known thing. It's very easy to see because we have that HNB is 90 degrees and HKB is 90 degrees, so we know that's a cyclic quad, and similarly for the other side, which means for the same reasoning we know that KHA is collinear. And furthermore, we know that the powers are the same, which means that A has the same, which means that WA times AF is equal to KA times AH. Or let me write that down for you guys. So WA times AF is equal to KA times AH. And therefore, we have that HFWK is a cyclic quad by the corollary of power of a point. In particular, I can't remember what the particular part of power of a point is called, but you can just say from the corollary or converse of power of a point, which means that we have that the angle HFW is equal to 180 degrees minus the angle HKW. Opposite angles sum to 180 degrees, but HKW is 90 degrees because it's perpendicular, which means that HFW is equal to 180 minus 90, which is 90 degrees, which means that H must lie on the line KY. Now, you must mention in this proof that in the case that W is equal to K, that this point F is just H, which means you don't need to bother with the whole cyclic quad argument, because that cyclic quad is degenerate, so it kind of breaks down there. But it's a small point, but you just need to mention it a little bit. Right. Now, that was the first problem. Now let's move on to the second problem. This is, of course, our little radical axis thing. Okay, so this, let's actually start this one again. So this is going to be the 2014 problem 4. Let's just bring that up over here. So we have points P and Q lie on the side BC of an acute angle triangle ABC, so that PAB is equal to BCA and CAQ is equal to ABC, and points M and N lie on the lines AP and AQ respectively, such that P is the midpoint of AM and Q is the midpoint of AN. Prove that the lines BM and CN intersect on the circumcircle of triangle ABC. Now, we know that we're going to need a circumcircle, so let's draw that. Let's put it over there, and again, let's get rid of these stupid names. Let's call it O, and let's call this again not, and then let's ignore it. Right, then we're going to need an acute angle triangle ABC. A, B, C. Then we have points M and N. Sorry, not M and N, P and Q. I'm just adding P and Q such that we've got some angle thing. So we have that. Let's look at angles. PAB, this angle here, must be equal to BCA. Now, I've clearly not drawn that diagram correctly, so what we're going to do is it's about there, but more importantly, we notice that this is a particular kind of property. This satisfies tan chord theorem, which basically means that AB should be tangent to the circumcircle of APC, which means we can just construct a circle that goes through AC that has a point on the perpendicular from A to B, and then take the intersection, and that'll be precisely our point P. So if we then get rid of these, we can then come up with a really good way to create a nice accurate diagram, if I can find my damn tools. So we construct that point, and then we want to construct the circle that passes that, so we're going to need a perpendicular bisector of this line, and then we are going to need a circle from this point to that point, and then this is our point B. And then we just hide all of our construction lines. And we'll don't need that either. Oh, let's get rid of that. And then we do the same thing on the other side. Construct a perpendicular line. Construct a perpendicular bisector. That point, and then let's hide all of our construction lines. I'm not going to need any of that. Then we're going to need to construct M and N such that these things are midpoints. So what we do is we will then make them lines. That we will then do circle. That we'll take a point, and then we will do a parallel line. We know that because of the parallel line, we've got that these are midpoints. So that is all that, and then we will hide this one. And we want to show that these lines intersect on the circle, which, as we can see by our diagram, they do. But let's just go about renaming everything so everything is in the right place. Let's get a point. This one, settings. Okay, so this one is P. This one is Q. This one is M. And this one is N. Now, this is quite a nice question because they've given us a lot of information. Actually, we're not going to need the circumcenter, so let's hide that as well. It's just cluttering up the diagram. Now, they've given us information about angles, so let's just write down what those angles are. In particular, we have, okay, so we have this one here is equal to this one here, and this one here is equal to this one here. And let's color these a bit so we know which ones we are talking about. And let's call this one blue. And unfortunately, they don't give me any way to make this bigger, but whatever. Maybe blue is not the right one, but let's go with it for now. now we notice we've got some similar triangles going on here because we've got a red and a blue in the base of APB, which means that APB must be the same angle at A. So let's just say that A is purple for now because you got the red and the blue. I'm not going to draw it in there because it'll just get too confusing. So, but we will put it over here. Oh, whoa, whoa. Okay, that's weird. And then we can do that one over there. And we know that also AQC is also going to be purple because the bases are red and blue. So we can make... Have I done something wrong? Oh, no, I haven't. It's just I'm not reading it properly. So these are both purple. And also A is purple as well. We must remember this. Now, also, the important thing is that we've given that P is the midpoint of AM, which means that AP is equal to PM. And we know that NQ is equal to QA, and in fact, they're all equal to each other because of the same base. So let us see what we get when we do some angle and ratio chasing. The idea would be to show that this point here, let's call it something, let's call it like E. E is fine. That E lies on the circumcircle, which is basically the same thing as saying ABEC is a cyclic chord, which is the same as saying that BEC is equal to 180 degrees minus purple. But we also know that NQC is 180 degrees minus purple. In fact, actually, let's give 180 degrees minus purple a color. Let's call it green, I think. Okay, we'll call that green. And so now let's look at some triangles. So the idea is that we've given midpoints, it seems like, and all these similar triangles, it seems like a good idea to start chasing some ratios. In particular, we have that this angle here, which is green, was also equal to this angle here, because, you know, just 180 degrees minus things. So let's do that, and let's make it green. So it seems only natural to think that NQC is similar to BPM or something to that respect. So let's chase the ratio PM over PB because we've got the angle in between it. So we'll take some text and we will take PM over PB. Oh, hang on, this is something. PM over PB. Okay, now PM over PB is equal to PA over PB, so let's just type again. So that's PA over PB. So PA over PB, but now we have that, we've got a purple in between and blue at the base and then red, so it's blue, red. So then that is the same as in this triangle here, CQ over QA. So let's write that, CQ over QA. Why isn't it not typing? CQ over QA. So CQ over QA, but QA is equal to QN, so that is the same as saying CQ over QN. Okay, so therefore we've got now two sets of sides in ratio with an angle in between, which means we've got some similar triangles. In particular, we have with P in the beginning, in the middle, we've got MPB is similar to CQN. So MPB is similar to CQN. That means that we've got some more angles that are similar, but let me just write that down. So MPB is similar, oh hang on, damn it, man. MPB is similar to CQN. So we've got some angles, we can put those in and we will give them a color as well. In particular, we have this one here, which actually we can call that one black, is the same as this one here. and this one here is the same as this one here, but they are different colors. In particular, this one we will say is orange, and this one we will say is also orange. So that means that green is equal to 180 degrees minus orange plus black. So there's green, there's orange, there's black, they sum to 180, but there's orange and there's black, which means that BEC must be green. Which is, if you will remember, exactly what we require, because green plus purple is 180 degrees, and that proves the problem. Now, an important thing in this question that you need to be wary of is that the positions of P and Q might not necessarily be like this. It's very possible that for a particularly weirdly, or is it only? Actually, no, for an acute angle triangle, it will always be like this. I think for an obtuse angle triangle, we get that it's for an obtuse angle triangle, what the hell's going on here? An obtuse angle triangle, they split, but for an acute angle triangle, they stay the same, and they've given us that it's acute, so it's fine. However, actually, an interesting problem, if you want to try, is that show that the same is true for an obtuse angle triangle. It is true, and it's very cool. Right, let's check how much time we have. Okay, cool. We have time for one last problem. So this last problem is the 2015 problem 4, which is a really long one, but, well, not a long problem. It's just a long statement. The actual problem's not that long. So we have a triangle ABC with circumcircle omega and circumcenter 0. A circle gamma with center A intersects the segment BC at points D and E such that BDEC are all different and lie on line BC in that particular order. And let F and G be the points of intersection of gamma and omega such that AF, BC, and G lie on gamma in this order. Let K be the second point of intersection of the circumcircle of triangle BDF and the segment AB. And let L be the second point of intersection of the circumcircle of triangle CGE and the segment CA. And then we've given that suppose FK and GL are different and intersect at the point X, and we have to show that X lies on the line AO. So, if we go about constructing this diagram, let's just duplicate a GeoGebra environment. I've already done it, but I'm going to just construct it so you guys can see how I would go about constructing the diagram. So we have a circumcircle, so we do that first. And again, we get rid of these names because they're going to interrupt us later. So we call that one O, and we call that one not, and we will just not show that. And then we have a triangle ABC. And then we have a circle with center A that intersects here at, whoops, hang on, let's do that a bit better. Intersects at points D, and we're going to have a point E there. Then this is point F, and this is point G. Then we will have circles through F, B, and D, and circles through G, C, and E. And then we've got points K and L over here, and yeah, G, H. So let's just give some to I, J, and then we don't have to bother about renaming these. So let's just select all of these and then go into settings and not show them. Now we want to show that if we've got the lines FK and GL, that they intersect on the line AO. And for ease of understanding, let's make this a dashed line. And let's just call this X. Now, the interesting thing here to note is that AO is the line between the circles, the line between the centers of the circles, gamma and omega, which means it perpendicularly bisects the line that runs between the intersection points. In particular, that is F and G, which means we know that this point here, which is called M, AMG is 90 degrees and FM is equal to MG. So therefore, Fx as Fk intersects GL on AO if and only if Fx is equal to Xg, which is the same as saying that Xfm is equal to Xgm. So let us look at what that angle is in fact equal to. So we notice one thing is that the one thing about this is that this angle isn't sort of well defined. We can't really chase this angle in any cyclic quad. So let's write this angle as a difference between two other angles. So in the cyclic quad KFBD, let's look at KFD, which we know is equal to KBD, which is just going to be angle B. And then we want to subtract this angle DF, whatever this thing is here. Well, in fact, it's DFG. Now, DFG is part of the cyclic quad FDHG, which means it's actually equal to GEC, which is equal to CLG. But actually, that's not really going to be super important right now. We're just going to call it, let's find the angle, let's give some colors in here. So and actually let's give some, yeah, okay, no, so we've got G, F, oh, hang on, whoops, have I done something wrong? Yep, I've done the wrong one. So G, F, D, that's going to be an important one. We're going to keep that one black, which is going to be G, E, C. And we are going to be talking about K, B, D as well. And we are going to be talking about L, C, E. Now, let us look at, let's just give these some colors first. So we're going to call this one red, which means this one is red. We're going to call this one green, and we're going to call this one orange. And then I think we actually need one more angle, which is going to be FDB, which is going to be equal to FGE because of exterior angle of a cyclic quad. And okay, those are going to be black, so that's fine. So we've got red, orange, green, and black. That should be enough for the whole problem. So we want to show that KFG is equal to LGF. Now we know that KFG is equal to KFD minus GFD, just because it is. And we know that KFD is equal to KBD, which is green, which means that KFG is equal to green minus red. So let's call that like G and R. So we've got G, R, O, and B, which are going to be green, red, orange, and black. So we want to show that green minus red is equal to orange minus black. Now, what is green minus red? Do we have any idea what that is? Well, actually, we can rearrange this. Equation to make it green minus orange is equal to red minus black. So these are the same equation by just taking orange to this side and red to that side. So red minus black, an exterior angle of a triangle is going to be equal to sort of this little acute angle thing here. If we extend these lines, G, F, and C, B, it's essentially going to be the angle that is formed between these two things. But in particular, we've actually got this semi-nice looking quadrilateral going on here. So it makes sense to look at what this angle and this angle is equal to, because then we'll be able to learn more about, say, what this angle is, just by comparing the two, the difference between them. So let's see how we're going to do that. So we know that O is the center of the circle, which means let's just draw this one here. And let's make it a dotted line just so ease of confusion. Now, we know that the angle subtended at the center by a chord is twice the angle subtended at the circumference, which means that AOB is equal to twice orange. And we know that AO is equal to OB because they're radii, so this is an isosceles triangle, which means that we know that angle OAB is equal to 180 degrees minus twice orange, all divided by 2, which is 90 minus orange. And we know that AMF is 90 degrees, which means that this point here is 90 degrees, which means this is actually, this small angle here is equal to orange. That's not gone well. Hang on. Again, not gone well. There we go. So we know that this is equal to orange. And actually, for the same reasons, we know that. Oh, it's not going to let me do that. Ugh, rubbish. Annoying. We know that that's going to be the green by exactly the same reasons. So let's fill in the colors. That is orange. That is green. Which means that this angle here, essentially, is going to be precisely the same if we look at the triangles. Or if you want to see that from a slightly different point of view, we have that in not cyclic quadrilateral, in just the quadrilateral MFDN, we will actually, let's just for a second, let us put in some text. Text. Let us call the angles at the bottom x, so that let's call FMN plus BN. Let's call that I don't know, D. No, not D. Have we used D? Yes, we've used D. Let's call it Z. For your favorite word starting with Z. Then the angles in FMND are going to sum to 360 degrees, which means we have the equation red plus 180 minus black plus Z equals 360. And in MPBN, we have that green plus 180 minus orange plus Z equals 360. And then by adding and subtracting those two equations from each other, we end up getting that the 360s cancel, well, I've just typed out black there, whatever. The 360s cancels, the 180s cancels, the Z cancels, which means that we are left with red minus black is equal to green minus orange. And that is precisely what we wanted to prove, which means that KFG is equal to LGF, which means that XF is equal to XG, which means that X lies on a O. And we are done. And that should be time. That is 45 minutes. And so yeah, hopefully that gives you a better understanding of what kind of problems you might see at the IMO. I fully expect you guys to ask me loads of questions in the Q&A, mostly probably about PowerPoint and radical axes. Please don't hold back. It's one of my favorite, it's probably my favorite theorem type thing, principle, whatever you want to call it, to use in geometry problems. It's ridiculously powerful. And so yeah, if you don't understand anything within the proofs, again, free to ask me. And yeah, see you guys later. Cheers.